Okay, we're gonna get started. So let's see, we are officially more than halfway through the semester, and if you've been following the book, remember the book, this one. Okay, we are already in chapter 9. So chapters 1 through 8 are more or less history. So we're in chapter 9, and I'm just curious, for those of you who've been, obtaining useful information from the book, what is in chapter 9? Okay, what do you see as the key ideas in chapter 9? And if you have not been looking at the book, then I guess this question wouldn't necessarily be very applicable to you. But for those of you who've been looking at, just obtaining, more reading material about the various ideas we visited in lecture. Okay, because I said many times already that, you listen to one person talking about something. Okay, well, especially in science, that's typically not sufficient, because you listen to me and okay, certain things make sense, but there are also things that maybe no matter what I do, it wouldn't be explained very well. So you would have to kind of think about it on your own and read someone else's written description of the same topic, okay? Or seek help. Go talk to a tutor, or come by my office and I'll try to explain things to you a little differently. Okay, so to give you a different perspective, okay? And many times that would be sufficient. You look at multiple ways of, describing a concept. And if you see some consistencies in these multiple explanations, I guess that means you have really understood what was being conveyed to you. And we're going to get into chemical bonding. And quite honestly, there's not a whole lot of concrete ways of looking at chemical bonds. Okay, it's not like I can give you, two things and give you a little glue and you glue the two things together. It's not like that. This is chemistry, right? This is molecular level bonding. So things are going to be, not directly observable. Even if it is observable in experiments, those experiments must be interpreted properly. I'll give you a very concrete example of what I'm talking about. Let's say you have carbon dioxide, right? So CO2, the formula, CO2, carbon dioxide. Carbon. So you know all these already, because you've taken Chem 115 and you survived through the first 2 exams. So CO2 means carbon dioxide. This is the name. This is the formula. Okay, so I'm going to give you like a box of carbon dioxide gas. Okay, so I give you a container. And what I'm going to do is I'm going to fill it with CO2 gas, okay, and nothing else. So I have just CO2 gas, okay? Then my next question to you is, how do you know that the carbon is bonded to oxygen? How do you prove it? That the carbon is bonded to the oxygen. You can try to talk to the CO2 gas, but it's not going to talk back to you because CO2 gas molecules don't talk. So you're going to have to do an experiment, right? Okay, so I'm asking, do you have any idea what sort of experiments will give us information about what's going on between, obviously we put a formula and we meant to have 1 carbon atom and 2 oxygen atoms all together in a molecule of some sort. This is called molecule. Molecule. So we know that C and O kind of, stick together. Okay, but how do you do an experiment that can, kind of prove this to you, that C and O are bonded? Yeah, that's it. Okay, that's a great idea. Just try to, I don't know, if this whole box has nothing but CO2 gas, why don't we try to just break apart the C and O, okay, and see how much energy is required, okay, in order for this to happen, okay. Well, that still does not really tell you the precise nature of this, so-called chemical bond, right? So in class, I drew these little, representation of a bond, right? And I just call this a bond. Okay, so precisely what is a bond? Okay, so you are suggesting, okay, we just blast the CO2, okay, and somehow we can measure, okay, the energy required in order to separate the C and O from each other. Okay, or in other words, figure out the energy required to, break these chemical bonds. Okay, then we have something to talk about, right? So you obtain what we call the bond dissociation energy. Bond dissociation energy. Okay, now what? Now, so okay, it takes so and so much energy to break, each of the CO bond. What are you going to do? So you determine the bond dissociation energy. And then what are you going to do? Well, how about this? How about study something else? Let's say you get a different sample. Okay, instead of CO2, let's do CO. Okay, because we know carbon monoxide exists, and we have an idea through some other kinds of analysis, not through this experiment in particular, but through some other kinds of it's called elemental analysis. I mean, you can just put a sample of a compound into an instrument, and then and then ask the instrument to kind of analyze what's in your sample, and it will just give you information about the presence or absence of different elements in the sample. So actually, there's a way that I can just stick in a little CO gas into an instrument, and have the instrument tell me what's in the compound, and then I'll get equal amounts of CO. So I know the formula is just CO, not CO2. And if I put CO2 in the same instrument, I'll get twice as much O than C, so I know it's CO2. So there are ways to determine these formulas, but it tells me nothing about the nature of the bond, okay, between the C and O. But I can do this experiment. Just kind of break up the CO molecule and figure out how much energy, or what is the bond dissociation energy for the CO molecule, okay? And then what do we do once we have both dissociation energies? I mean, obviously, we're going to, what seems to be reasonable to do next? We compare them, right? Right? Does that seem reasonable? Okay, so you get the bond dissociation energy of CO, and you get the bond dissociation energy of CO2, and then I'm going to compare. Okay, and it turns out that one is higher than the other. Okay, the CO require more energy to break the bond than CO2. Okay, to break the same bond, CO bond in CO2. So what does that tell you? Yeah, it requires more energy to break the CO bond in carbon monoxide. So the bond energy is higher. There's a stronger bond between the C and O in carbon monoxide than the CO bond in CO2.
Because of equal amounts.
Huh?
It's because it's equal amount.
Well, because it's similar atoms, a bond between two similar atoms, it's between C and O, right? In two different molecules. So one is the CO molecule, the other one is the CO2. Okay, whatever is going on here, okay, compared to this one. Okay, I know the CO bond energy. Okay, well, this is going to get a little messy because we have two CO bonds, but one is in CO, the other one is actually in CO2. So actually, what I need to do is make a table. Okay, so you can compare. Okay, so I'm looking at the CO bond. Well, I guess. Let's see. Yeah, I mean, we're looking at the CO bond. Okay, dissociation energy. Right? CO bond dissociation energy. And then you have this in a molecule of CO. And you also have that in a molecule of CO2. So you're looking at, whatever this number is compared to this number. And then you can figure out which one is bigger. Right? So if this is bigger than that, okay, it is giving you information about the nature of this bond compared to the nature of this bond.
Can you draw them on the configuration of the Lewis dot structure?
Yeah, the Lewis dot, yes. I think that's a very bright idea because that's exactly what I'm getting into. See, the carbon monoxide look like this. Carbon dioxide look like this. Okay, and you can put the lone pairs on the atoms. Okay. I mean, I trust that you attended lab and you got an introduction to the construction of these diagrams. Okay, I don't expect you to know right away how to draw all the diagrams for all the compounds, because you have to imagine, right? There are millions and millions, tens of millions of compounds. So I don't expect you to immediately be able to draw all these diagrams for all the compounds. Okay, start with the simple ones like CO and CO2. In fact, these are good ones to memorize because you see them so often. Right? Carbon monoxide. Okay, just memorize. Okay, you have C and O and the 3 lines in between them, and then the C and O in CO2 has only 2. Okay, so I mean, how do we end up with these diagrams? Right, for carbon monoxide and carbon dioxide, that really give us a concrete description of the bond, right? I mentioned bond, not James Bond, chemical bond. Okay? I mentioned, chemical bonds between atoms. This is precisely what we think is going on.
So did they tell us something about the relationship they have? I wanted to say, because when I see bonds,
right,
and we talk about what kind of energy does it take to break the bond, I think about the relationship on the periodic table in regards to electronegativity.
Okay, well.
Because wouldn't one have more of an oxygen have an affinity for carbon?
Well, okay, you are leading into some other concepts, okay, which I'm glad you brought up, even though it may not directly relate to what I was trying to do over here, because this is purely, bond dissociation, okay, meaning that, okay, if I want to break this bond, it's going to cost me more energy than to break this bond right here. Yeah, that's right. So I can say something like, bond strength. Okay, that's what we're getting into right now in lecture. We are going to start looking at bond strengths.
It would take more energy.
Yeah, it would just
to break 3 bonds.
Yeah, right. A triple bond. Yeah, it would take more energy to break a triple bond than to break a double bond. Okay. Now, is it all the time? Not necessarily. You could have, some kind of a triple bond which is easier to break than another double bond. But here the comparison is more direct because you have just the C and O, right? You could compare the N triple bond to something like, well, maybe not the NN. Yeah, actually, that's okay. NN triple bond compared to I don't know, NO double bond. Okay, I mean the comparison here becomes a little bit more difficult, right? Because you have, one is a bond between 2 nitrogen, the other one is a bond between nitrogen and an oxygen. So I may not be able to directly compare these two unless I have data. But you cannot just say, well, this is a triple bond, this is a double bond, so it's always going to be more energy required to break this one than this one. Because we're looking at almost like two different situations here. While here, clearly it's C and O, C and O. So you cannot just, like what you suggest, look at the electronegativity and then determine the bond dissociation energy. You have to do the experiment, right? Collect the data, and then you'll be able to say, okay, clearly it requires more energy to break the C and O bond in carbon monoxide than the C and O bond in carbon dioxide. So in this case, we can kind of make a simple conclusion here that a triple bond is stronger than a double bond in general. Okay, and what you're referring to in terms of electronegativity, okay, that's actually a related concept, but it does not apply directly here. Okay, it does not it does not apply directly to the comparison of bonds. But I guess let me just say one more thing before I go on and talk about electronegativity, since you brought it up. We have not even covered this in lecture, but that's kind of what we are heading into, the concept of electronegativity. Okay. So what I was trying to say here is that we collect information about molecules, and then we try to compare different bonds, okay? Because different molecules tends to have, obviously, if the elements are not, if you're looking at two molecules, they don't have the same elements. Like if you're comparing CO2 to NH3, obviously you're comparing NH bond with CO bonds, okay? So, that makes things difficult if you really, compare very different elements in the way that they bond together. But what we're trying to do is, we'll try to collect as much data as possible on similar compounds, okay, on similar molecules, and see if we can determine a pattern, okay? And so far, what we've been seeing by at least looking at these bond dissociation energies is that we will notice a general pattern, okay, which is that whatever we call a single bond, okay, and I can give you a more concrete example of what is called a single bond. In the case of like a CH4 molecule, okay, and again, I'm glad that you brought up Lewis structure right away, because it's a very powerful tool we use in chemistry, obviously, because Lewis structure explains, or at least gives us a model to explain the way that different atoms can be bonded together to form molecules. So this is what we refer to as a single bond. Okay, and single bond is basically the sharing of how many electrons? Two. Yeah, sharing of 2 electrons between 2 elements. Okay, and a double bond is sharing of 4, right? 4 electrons, and a triple bond is sharing 6. Yeah. Okay, that's how they're defined. But these are ultimately just models, okay? And Lewis' model seems to be a pretty good model, even though sometimes it fails. Okay, this is not universal. The organic chemists, okay, use Lewis structure very often because, amongst the elements, carbon, oxygen, hydrogen, and nitrogen, very few exceptions exist. Okay, so as long as you stick to the rules of constructing Lewis structures, okay, the basic rules, then you don't need to worry about the exceptions too often. Okay, but for inorganic substances, okay, which involve basically the rest of the elements, other than the ones that I just wrote down on the whiteboard. Right, you're looking at inorganic compounds. Okay, the exceptions are so observable. There's so many exceptions that you almost have to create a different system, a different set of theories, just to explain all those organic compounds. So if you ask me, is Lewis structure a very powerful kind of model? I would say yes, but it's more like for organic chemists, okay, or maybe just basic inorganic. But there are so many exceptions to so many elements, other than the ones that are typically found in organic compounds, the C, H, N, and O. That you have to be very mindful about the use of Lewis structure. Okay, so let's talk about electronegativity, which is actually section 9.1, I think, of your. Let's see. No, not 9.1. It's or maybe it was in chapter 8. Yeah, chapter 8, chapter 9.5, section 9, section 5, chapter 8, on top of that. Chapter 9, section 5, 9.5. That's the section where it links with electronegativity to chemical bonding. Okay, so first of all, we need a definition for electronegativity, because a lot of students tend to talk about it without knowing exactly what it means. Okay, electronegativity. Okay, so in your mind, what does that mean? What is the meaning of this term?
When I think about electronegativity, I
Mhm.
think about this electron affinity. But
Oh, okay. You brought up just another often misunderstood term, electron affinity. Yeah, that's good. But these two are similar but different. Okay, so these two are not the same. Okay, but going back to electronegativity, what do you think of when you use the word electronegativity or electronegative? What do you really see yourself trying to express? What kind of ideas?
strength,
Huh?
the strength of that atom.
Okay.
Like, I know the electronegativity of elements to the right are going to have a higher electronegativity than elements to the lower left.
Right, right. So what does that tell you?
That when they get into some type of relationship, that element on the right is probably going to have it's like he's gonna demand, hey look, take these electrons, get them here.
Yeah. Well, I think you're getting.
Electrons using
Well, that's something else. Actually, that's something else. Well, electronegativity is actually a very interesting idea. Okay, which, well, if you just think of a general situation, right? Let's say there are two different elements, and I don't mean X or Y to be any specific element, just two different elements. Okay. And let's say they're going to form a chemical bond. Okay, there's some kind of chemical bond between them. Okay, so and I measure the electronegativity. Okay, of one of the two elements. So let's say I measure the electronegativity of this element. Well, what does that really tell me? Okay, so I know the electronegativity of X. What does that tell me? Well, that tells me how much the element X wants to attract the shared electron to itself. Okay, so first of all, you have to assume that X and Y are bonded together, right? And then the next question is, Okay, I want to find out how much X wanted these electrons to accept. So we have to kind of, you know, almost kind of take it for granted that there's something which is called covalent bonds. Okay, and I know covalent bond is typically being referred to as the sharing of electrons. Okay, so if two elements, X and Y, I guess, in my example, if they share electrons, then you know that's basically a covalent bond between them. Okay, so we almost have to just accept the fact that two elements can be bonded covalently. Okay, and then we ask the next question: okay, how much at the element X wanted to, you know, attract the shared electron to accept? Okay, so that's called the electronegativity. Now, how is that different from electron affinity? Well, electron affinity is very different. Okay, so let's say you have element X, right? And I don't really want to know how X and Y are bonded together. But if you have this element X, okay, you just want to add an electron to this element to form this ion, X minus. Okay, and I think by definition, the electron affinity measures the energy given off in this process. Okay, so you're just going to force an electron into any element. Okay, so energy given off or release, I guess that's the more elegant word. Energy released. In the process where an electron is added to an element, to a neutral element. So where an electron, just one electron, where an electron is added to the atom, to the neutral atom of an element, to the neutral atom of an element. Okay, whereas here, okay, the electronegativity actually refers to, you know, two things that are already bonded together. Okay, and you're looking at by how much one particular element would like to, you know, hold on to these shared electrons between two elements. Okay, I tend not to, you know, necessarily relate electronegativity with anything like, you know, single, double, or triple bonds, because the two are very different ideas.
What about sodium chloride?
Well, okay, so if you have sodium chloride, what about it? What about sodium chloride?
I mean, they both go, one's on the one end of the chart and the one's on the other end of the chart. Sodium is, so you got two electrons in it?
Yeah, that's right. That's right. Well, sodium has only one, actually. Okay, while chlorine has 7. 1, 2, 3, 4, 5, 6, 7. Okay. Okay. So, do you think that they can just share 2 electrons to make a single bond like this? Okay. Why not?
There's going to be more. There needs to be more bonds. Correct. You're gonna have more chlorines.
More chlorine. Okay. So you mean what? You mean that there are
Sodium needs to complete its shell. So the shell needs.
right, but it's
more
out of electrons already. It had used to have 1, and now it's sharing 1 with
So it
chlorine.
has no problem giving up the one.
Okay, so now we're talking about a totally different kind of chemical bond, right? You're saying, okay, sodium would rather just get rid of its one single electron to form Na plus. Okay, and here, chlorine used to have 7 electrons. Now you're going to stick one more electron into the chlorine atom to form chloride. Right? You see how powerful it is for these Lewis structures, because it really just kind of put abstract ideas in a concrete picture. Okay, so now chlorine becomes chloride. Okay, instead of having 7 electrons, or 7 valence electrons. So this is where the word valence comes in, because chlorine has more than 7 electrons, right?
But the chlorine is saying, I need that electron, give it here, and sodium saying, okay, you can have it, because he has an attraction to need more electrons. Chlorine does, and sodium does. Sodium has no problem, he don't mind giving it up.
Right, but why is that? Why is sodium does not mind giving up the only valence electron it has? And why would chlorine be interested in that electron?
Has that something to do with electronegativity?
No. It does not.
Wouldn't that make the valence for the chlorine stronger?
Yeah, that's right. That's why chlorine
That's why
prefers. Well, it makes it stronger, but again, stronger is your way of saying it. Okay, the way that books in chemistry or the chemists like to use to describe this idea is called octet. Okay, this idea called octet. I mean, obviously, OCT reminds you of 8, the number 8. Okay, octet means a set of 8 of something. Okay, well, applying to these diagrams, right? The rule of 8 refers to rule of stability when something has 8 valence electrons. Okay, and it doesn't really matter what. I mean, there are many elements, especially the main group elements. Okay, they tend to follow the octet rule pretty well. Okay, the main group elements, what am I talking about? The ones in the A group, 1A, 2A. If you look at your periodic table, you're going to see these, various kinds of group numbers. 1, 2, 3, 4, 5, 6, 7, 8, 9, so just go. Okay, there's no group 9A. I guess 1, 2, 8, 1, 2, 3, 4, 5, 6, 7, 8. That's it. Okay, these are called main group elements, and they pretty much obey the octet group. Again, you talk to these elements, and try to get these elements to talk. They don't talk. Okay. So the only way that you can find out about them is to do experiments. Okay, so you measure things like this. You measure the electron affinity of something like chlorine. Okay, so you get yourself a chlorine atom which has only 7 valence electrons. Okay, so these are all valence electrons, and this is a representation of the chlorine atom. Well, why do I call it a chlorine atom? In fact, I might want to even call it more specifically a neutral chlorine atom. Okay, because even though only 7 electrons are shown, there are actually more. But what I know about this atom is that there are the same number of protons and electrons in the atom. Okay, but what if you just add one more electron to the chlorine? Okay, now you have instead of 7, you have 8 valence electrons. Okay, so we measure the electron affinity of this process, right? Just adding one more electron to the chlorine atom to form Cl-. Okay, and we kind of measure the energy released in this process, right? And then we compare, right? Measuring the electron affinity of one element does not really tell you anything, right? It's just a number. But if you measure the electron affinity of all the elements, then that tells you something, right? So you compare chlorine to something like, what is the element to the left of chlorine? Is it sulfur, something like that. Yeah, sulfur. Okay, so let's compare chlorine to sulfur. Okay, so sulfur is the element to the left of chlorine. I mean, it has one fewer proton, one less proton. Okay, also one fewer electron, I guess. So here we have 1, 2, 3, 4. I guess if you put the 6th dot on the sulfur. Okay, so this is sulfur, the element sitting to the left of chlorine, and you try to force one more electron into sulfur. One more. So you try to force one additional electron from somewhere, I don't know where. Okay, let's just pretend this electron can be obtained somewhere. So I'm going to force this electron into sulfur. Okay, so now it has 7 instead of 6. And again, I measure the electron affinity. Okay, so I measure the electron affinity of both. And I realize that the electron affinity is actually higher for chlorine. Okay, it's not as high for sulfur. Okay, and then you go look at the next element, which is phosphorus. Okay, 1, 2, 3, 4, 5. Okay, phosphorus has 5 valence electrons. So you try to add one more electron to phosphorus to form this. Okay, the one with one more electron. Okay, so this one is the sulfur minus. This is the phosphorus minus. And we realize that the phosphorus minus released even less energy. Okay, this one released the most, and then this one is a little less. This one is even less. So we have no choice but to start, start making hypotheses about what's going on. Okay, and that leads us to something which, as we know it today, is called octet, because adding one more electron to chlorine create an octet for chlorine. Okay, adding one more electron to sulfur or phosphorus does not do as much to what? To kind of, to increase the stability of the species. Okay, and when I say the word stability, immediately you should be thinking about also energy. But this is not kinetic energy. Every time I mention stability, it refers to potential energy. So I'm not talking about, okay, you're squeezing more energy into something. Okay, I'm just looking at, okay, chlorine without the additional electron has this much potential energy. Okay, I force another electron into chlorine to make it chloride, and then all of a sudden the potential energy dropped by a lot. So we thought, okay, well, what's going on here? Okay, how come it's more stable this way than this way? Okay, and the best idea we've got is, okay, well, maybe 8 is a good number of valence electrons. Okay, somehow, for some reason, 8 electrons enhance the stability. 8 valence electrons enhance the stability of that something we're looking at. Which also explain what? Which also explain why the noble gases, they are very much inert. Something like argon, okay, which is known as a noble gas, argon. It's known as a noble gas, okay, or inert gas. So take a look at the position of argon on the periodic table. Right, it is in right to the right of chlorine. Okay, so to the right of chlorine you see argon on the periodic table, and it has 18 electrons. Right, so if you go back and look at the electron configuration of argon, 1s2, 2s2, 2p6, 3s2, 3p6. Okay, so take a look at the number of valence electrons. Okay, of valence electrons, 8. Okay, and we know that argon is very, very inert. Okay, you try to react argon with some other elements or compounds, it just don't react. Okay, so this is another piece of evidence. Again, these bonds or these molecules, they don't talk to us. Okay, we have to kind of do our experiments in order to find out something about them, and you know, or even if you don't do experiments, then at least make observations. You know, make very careful observations about the properties of these different elements. Yeah.
Yeah, well, I have a question. I noticed that, for example, so you know you jot down the dots separately.
Mm-hmm.
Why is that? Is there a
Oh, that's just you know, because that's conventionally how we represent these elements using a dot diagram. I mean, there's nothing wrong if you place the dot in a different way. Like if you draw sulfur, right, and you try to represent that sulfur has 6 valence electrons. So you put 1 dot here, 1 dot here, 2 more over here, 2 more over here. There's nothing wrong with your diagram compared to this one.
I just went out.
Okay, I mean, even if you pair these up, this is not wrong. But what I know is that, you know, sulfur is kind of like oxygen, right? Because they're in the same group. Okay, oxygen also has 6 electrons. But what does oxygen like to do? Is to form 2 bonds, right? So that's why I put 1 dot here, 1 dot here. So when the hydrogen comes in, there's another hydrogen. The hydrogen has only 1 electron. So maybe these 2 can share, and these 2 electrons can be shared. So these 2 are now shared between the oxygen and hydrogen here. And let's put this as H1, this is H2. So these 2 electrons are shared between H1 and O. These 2 are shared between H2 and O. Okay? So kind of, you know, that's how this evolved into a Lewis diagram for H2O, which looks something like this. So I'm just kind of, you know, putting the oxygen here, putting 2 dots, and 1 here, 1 here. Kind of anticipate that there are going to be 2 single bonds. Okay? So other than that, I mean, there's no particular reason. I mean, there's no rule against putting the dots somewhere else. But we kind of like to, you know, pair them up as much as possible, unless you know, pretend that, okay, oxygen is going to form 2 single bonds. So I just, you know, put 2 long electrons on either side or on the top, bottom, doesn't really matter. Okay, I mean, even if you draw the Lewis structure of H2O like this is not wrong. I mean, I don't know why, you know, you think this is wrong. This is still the same Lewis diagram that represents the water molecule. Okay, but again, I want to emphasize this is an idea which is called octet. That elements like to, you know, have 8 valence electrons. That's an idea called octet. Has nothing to do with electronegativity. Yeah.
Can you go over the way to determine how many bonds? You know, there's a math thing we do, charts and everything.
Mm-hmm.
Where you can determine how many bonds it's going to actually be. Like when we were in lab, we were doing
Right.
chemical, electrochemical, and look at it. You can look at it and say, oh, okay, I can tell it's going to be 2 bonds or it's going to be double bond or whatever. But
Yeah, there are some, right.
there's a way that you can do it. You can.
Well, I think there is. There is a formula. There's a formula that you
It's
can.
like a chart.
No.
Your valence electrons and the octet electrons. And then, like if it's a plus or minus, if it's a plus.
Well, there are a lot of things going on. I agree with you. There are issues of, you know, so I guess I'll go back to mention a little bit more about NaCl, because, you know, you asked me about NaCl, and we are kind of halfway through it. But now you're asking, okay, how do I draw a Lewis structure? Right? That's what you're. Okay, and you just said a bunch of things. You said, okay, you have to count the total number of valence electrons. right? And then somehow you have to determine the number of bonds. Number of bonds. And I know you mentioned about charge, so you have sometimes you draw a structure for non-neutral species. So let's say you have to, well, let's forget about the charge for now because it does not really matter. Because as long as you can count the total number of valence electrons and determine the number of bonds.
When you're done, you'll know exactly how many bonds you need. So aside from guessing, I think I might need a bond here, a bond there. You'll know I need 6 bonds, whatever, and
yeah.
so when I only need 6, why do I have 7? Something wrong.
Well, let's see if we can look that up in the book because personally I don't use that formula, and I'll tell you why. So, but since you're interested in the formula, let's see if I can kind of look that up. That's not even in chapter 9, that's in chapter 10 or 11. This is 10, I think chapter 10 is.
Lewis formula?
Yeah, a formula that helps determine the number of bonds in a molecule.
You don't have to use it though?
No, I personally I don't use it very often. In fact, I don't remember it. That tells you I don't use it.
Right.
No, you know what? Your book does not have that formula.
Start off, see, Professor Zeno, we start off with write your formula, like you have your formula. And then you follow up valence electrons.
Right.
Our book talks about it briefly, and total valence electrons, whether it's 20 or whatever. And then next column, you octate electrons. That would be what you actually need when you subtract. And if you divide, I would say like 2, you got 2 elements.
Okay.
And you'll come up with the number of bonds that you have, that you're supposed to have.
Right. Yeah. I see where you're going, and I've seen that kind of formula or algorithm being applied, and it's it kind of works some of the time. Okay. The reason that I don't prefer formulas is because now, what if something is an exception? You try to do a calculation using a formula, and then you're looking at an exception, something like BF3. The formula does not really apply, but if you just kind of work on the boron as the central atom, I think it makes a lot of sense to do this. Try to identify the central atom.
For less valence electrons.
Yeah, typically that's the element, the fewest valence electron. But there are certain ways you can kind of determine that. CH4, the carbon is in the center. CO2, put the carbon in the center. But there are also times where like let me give you this. Well, let's say HF, hydrogen 4. It does not have a central atom because it's just 2 elements bonded together, and you could have I'm trying to think of something that.
I don't want to take all our time on that.
Now this guy SCN minus. Okay, do we put the carbon in the middle, the sulfur, or the nitrogen? So there are also times when the central atom is difficult to determine. There are most of the times when the central atom is fairly, fairly visible. So, yeah, but I would, kind of use the formula if you feel more comfortable with the formula. But also kind of look at the situation right here. Put down the central atom and, and see where the other elements is going to fit around the central atom. So you put and you know certain things about these elements. Right? You know fluorine has 7 electrons, 7 valence electrons. Right. So it needs to form a single bond, and it's going to do it by sharing with boron. And likewise over here, you share it. So there's no need for that formula. You just kind of, look at what the elements like to do and, work out a structure, a potential fluid structure. It may not always be correct. You could be looking at a wrong structure, but at least you have an idea that you draw this, and you have something to do with, so that you can kind of expand on it and double check and make sure everything seems to be in order and so on and so forth. Well, I just want to go back to the sodium chloride before I forget. We talk about electron affinity, right? Adding an electron to an element, and you measure the energy being given off, and you realize that chlorine really likes to be chloride instead of being chlorine. Okay, or in other words, chlorine would rather have 8 valence electrons instead of 7. Okay, so we collect all these ideas, and then we start to kind of make sense of what's going on in NaCl. So sodium, right? Why would sodium be so interested in giving up its only valence electron? Well, because if you look at the electron configuration of sodium, it's 1s2, 2s2, 2p6, 3s1. Well, with that's right. With the additional electron, then it has no octet. But once sodium becomes Na+, so sodium becomes Na plus electron. Now take a look at the rest of the configuration. We have, 8, outer shell electrons, or 8 valence electrons.
So by itself is not, I guess the word I would say is not balanced.
Oh, you can say that, yeah. By itself, it's not stable. Like the stability idea, right? And the more you use the term, the more you'll be used to it. Yeah, right now you can say it's not balanced. It's not comfortable, right? But by giving up an electron, okay, Na becomes Na plus, which has this electron configuration, which shows you the valence shell of Na plus has 8 electrons. Okay, so no wonder. Okay, the ionization energy. This is something I started talking about in the lecture. Okay, the ionization energy of sodium. Why is it so low? Okay, I mean, you compare the ionization energy of sodium, and you compare to the ionization energy of something like chlorine. So let's say you have the chlorine doing the same thing, or similar thing. So you put the chlorine here, which has already 7 valence electrons. 1, 2, 3, 4, 5, 6, 7. Okay, and you're going to do the same thing. Try to remove 1 electron from chlorine. Okay, doesn't matter which one. Okay, so you try to remove 1 electron from chlorine, and you notice the ionization energy for this is enormous. Okay, so I mean, if you want actual number, I'm going to see if I can just look that up. It's in your book already. I mean, all these various elemental properties, they are summarized in your book. So I'm looking at figure 8.16. Okay, so look like chlorine requires 1,256. 1,256 kilojoules per mole of energy to achieve this. Okay, to pull 1 electron from chlorine. And for sodium is 496. kilojoules per mole. Okay, obviously, joules is an energy unit, and in chemistry we don't usually operate per atom because how do we measure the energy per atom is very difficult. So we get 1 mole of atoms together, okay, and we measure the energy in kilojoules. So the ionization energy for Na is 496 kilojoules per mole. The ionization energy for chlorine is 1,256 per mole, kilojoules per mole. So there's a huge difference here, okay, between the ionization energy of sodium and chlorine. So, and then you kind of also look at the second ionization energy of sodium, right? So let's say you pull another electron from sodium, or at least you try. Okay, now you have 2s2 to p5. And the second ionization energy, let's see if I have a number for it. Yeah, actually, no, I think this is it. 4,000, no, 4. Hope this is right. It's 500. This is 4, 5, 6, 0, 0. Right. Oh, 4, 5, 6, 0. Times okay, 4560. Okay, 4560 kilojoules per mole. This is according to the data in your book. So to remove the first electron from sodium, or so-called the first ionization energy of sodium, is 496 kilojoules per mole. But if you try to pull the second electron away from sodium, it's going to be almost 10 times the amount of energy in order to take the second electron away. Okay? So, I mean, you want to take 2 electrons away from sodium at the same time, and just add these 2 numbers. Okay? But it shows you, right, if you have already 1 electron removed from sodium, okay, the stability is not comparable to this one when you had 2 electrons removed from sodium, or a second electron being removed from sodium, because it's so much harder to remove that second electron. It tells you how stable it is for sodium to be, without its own valence electron. Okay, so once again, it kind of reinforced the idea that number 8 is a good number. Okay, rule of 8 is a good rule of thumb. Okay, we call this the octet rule. And so hence you have the sodium ion being a stable ion. And you have the chlorine ion also being a stable ion. So Na plus is stable. Okay, Cl minus is also stable. Okay? And I mean, normally you would just have these stable ions, but obviously, because each of these ions has a net charge. I mean, I know sodium has so many protons and so many electrons, right? But having an equal number of protons and neutrons and electrons, okay, result in what we call a net charge being placed on that something, okay? So there's a net positive charge on the sodium ion. There's a net negative charge on the chlorine ion, okay? And these net charges interact, okay? And this is what we call an ionic bond. Okay, when ions attract each other, that's called an ionic bond. And like, I thought you were going into something like this. How come we don't, continue to write plus and minuses? Okay? In fact, this is very much true. I mean, if you just keep writing plus and minuses. You could easily, have millions and millions and millions of these ions. Okay, and this kind of explains why ionic compounds are often exist in crystalline forms. Okay, because these ions tends to be, pretty orderly arranged. Okay, like sodium chloride. Normally you would think of sodium chloride as crystals, right? So you have these plus and minus at the corner of cubes. And these are, imaginary cubes. These are not real cubicles, but you can always imagine that these ions are just going to be so effective in terms of attracting each other. This, okay, that it would have an extended structure. Okay, you can extend this structure very easily, and then explain why ionic compounds are usually crystalline. So let's see, can spell crystal anymore. C-R-Y-S-T-L. So this is what I want to say about ionic bonds. Okay, so where's the electronegativity? Actually, I'm afraid it's not very applicable. Okay, because electronegativity refers to very specifically, okay, two elements that are already bonded together. Okay, and how much one element wanted the electron more than the other. It has some implication, I must admit. Okay, as far as predicting the types of bonds, and because this is how high school teach chemical bonding, is you look up the electronegativity of different elements. Okay, like sodium, I can easily look up the electronegativity, which is if I can just get to the right pages. Well, sodium is 0.9. Okay, the electronegativity of sodium. Well, what is the unit of electronegativity? Nothing. Okay, it has no unit. So it's clearly not the same as electron affinity, because electron affinity actually is in units of kilojoules per mole. Okay, the ionization energy obviously also has units of energy, kilojoules per mole. Okay, bond dissociation energy has units of energy. But electronegativity does not have energy units. In fact, has no unit. Okay, it was just some sort of a scale that was developed by Linus Pauling. Okay, in trying to explain. Okay, well, yes, we have all these bonding theories already. We have Lewis structure, we have octet rule, and we seem to have a good understanding of the difference between ionic and covalent bonds. But yet, maybe there's a scale that we can put into use. We can develop for all the elements, so that somehow we learn something about the behavior of these given elements. So if you look at the electronegativity of sodium, it's actually 0.9. And if you look at the electronegativity of chlorine, it's actually 3.0. Okay? And so you have to kind of understand the electronegativity scale goes all the way from pretty much 0, okay, to about 4. Again, it's a very arbitrary scale. If you want to, think of, if you want to invent a different scale, okay, I guess you would have to justify it. You have to teach everybody else how to use it. But otherwise, it would just work fine. Okay, there's no reason for the number 4 to be the terminal, the highest possible, electronegativity value. If you can redefine the electronegativity idea, I mean, not necessarily redefine the whole idea, but just think of a way to kind of stretch out the scale or condense the scale. It would work just the same as the scale we have today, which is pretty much all the way from 0 to about 4. So chlorine is 3. If you look up chlorine electronegativity, and sodium is 0.9. Okay, so I guess hypothetically, right, if you have NaCl forming a single bond, a covalent bond, then chlorine having a higher electronegativity value would pretty much tell you that, okay, in this particular situation, chlorine would rather keep the electrons to itself, okay, than sodium. You know, sodium doesn't care, okay? You know, it's perfectly all right for sodium to not have as strong an attraction to the two electrons being shared between them than for chlorine, okay? So I guess in high school you're being taught, well, you can compare these two numbers, not add them, actually subtract them. If you have sodium and chlorine, you take 3 minus 0.9, always the bigger minus the smaller, and you get 2.1. Right? That's called the difference in electronegativity between the two elements. And what are you going to do with 2.1? Well, you're going to look at some kind of a scale, right? Okay? And the scale might look like this. Okay? The scale is, well, for an ionic bond to be formed, okay, the difference in electronegativity has to be what? You remember from high school? 1.7 or higher, something like that, if I remember correctly. I mean, these are very arbitrary numbers. Like, there are plenty of cases where, you know, the scale just does not work or fail to work because you know, the difference in En becomes so, you know, ambiguous between some of the pairs of elements. Like for covalent, in fact, you know, the more appropriate description here is polar covalent. Okay, now so we introduce the word polarity, which confuses a lot of people, you know. So what is the difference between, you know, polar covalent and non-polar covalent? Right, but according to this scale, polar covalent is somewhere between what, 0.5 to 1.6, and therefore, you know, if you have something, I mean, delta En, if you have a difference in electronegativity between the two elements, which is 0.5 or lower, then it's considered a covalent non-polar bond or non-polar covalent bond. So you can start applying this scale to you know, pairs of elements. Okay, so for NaCl, it's pretty easy. Just if you put sodium, right, you put Cl and you look up for sodium is 0.9, for chlorine is 3.0, so the difference, which is the delta En, equals to 2.1. So you go to the scale over here and you said, okay, well, 2.1, which fits in the 1.7 or higher category. So no wonder NaCl forms an ionic bond. Okay? Or look up for sodium and aluminum. So let me look up the electronegativity of aluminum. Is it 1.5? Okay, so what kind of bond should be formed between sodium and aluminum? Okay, so I put the, let's see, aluminum. You said this is 1.5 for aluminum. Okay, so 1.5 minus 0.9 is 0.6. Okay, so 0.6 seems to be here, right, between polar covalent and non-polar covalent. But do you really think that sodium and aluminum would form a covalent bond?
You rarely hear about those two.
Right, they both matter, but they don't form covalent bonds. Okay? Because covalent bonds are formed between what? Between two non-metal elements. So between hydrogen and oxygen, or between carbon and oxygen, nitrogen and oxygen, or nitrogen and hydrogen. These are all non-metal elements, so they like to form covalent bonds. Okay? But you know, two metals, they like to form ionic bonds or metallic bonds. We haven't talked about, there's not even mentioned here. You know, the idea of
It's the other way around.
metallic bond. What? The other way around? Okay. Yeah, I mean, I have not even mentioned metallic bonds. I mean, these are both metals. Okay, why don't they form a metallic bond together? Makes sense, right? Okay, but according to the electronegativity difference, it's 0.6. The 0.6 is, it's polar covalent, but you gotta have some idea what these elements really are in order to apply it. I mean, in order to interpret the scale appropriately, because otherwise, if you just focus solely on, the difference in EN, okay?
Sulfur and oxygen. Sulfur oxide.
Yeah, okay, so yeah, that's right. If you have sulfur and oxygen.
That's a covalent bond, right?
Yes, that's right. But furthermore, if you look up the electronegativity of each one, sulfur is something like 2.5, and oxygen is once again 3.5, is it? 3.5, yeah, so it's 1.0 difference. But you know that two nonmetals tends to form a covalent bond anyways. But this is telling you that, okay, maybe the bond is a little bit polar. So this one becomes a polar covalent bond. Okay, but in principle, this is just a covalent bond. Okay, except that oxygen with a slightly higher electronegativity, it implies that the oxygen would like to attract the shared electron to itself a little more than sulfur. Okay, which is why the bond is polar, because it's no longer shared evenly, the electrons. So if you imagine that sulfur and oxygen has a single bond, okay, so the oxygen has a high electronegativity, which says that, okay, the oxygen likes to, instead of sharing the electrons evenly with sulfur, oxygen would rather, hold on to the electron to itself, okay, leaving sulfur without the, the shared electrons, okay, which creates a situation here because now, the oxygen is thought to be partially negative, and the sulfur is partially positive. Okay, this symbol right here looks like the letter S, but it's actually not the letter S. It's called delta. It's just the lowercase d in Latin. Okay, it's called delta. I mean, this is the capital D. This is the lowercase d. It's called delta. They're both deltas. Okay, but the delta indicates partial. So in books, okay, and in fact in class, I'm going to start using the symbol delta. It indicates partial. Okay, so it's not like a strong charge on something, like the case when you have sodium Na+ and chlorine Cl-. I mean, this is not meant to be partial charges. These are net charge, and these are a lot bigger than the charges over here that we place on these polar covalent bonds. Okay, like we put the partial negative on the oxygen, put the partial positive on the sulfur, and that explains why there's a polarity here, because apparently things are not even. So we have two poles. We have the positive pole and a negative pole. Okay, but fundamentally this is just a covalent bonding situation where the S and O are covalently bonded together, but the shared electrons tends to spend more time around the oxygen nucleus rather than the sulfur nucleus, and therefore creating the uneven sharing. So we call this a polar covalent bond. Versus, if they share things pretty evenly, like in the case of the OO bond, the O2 molecule look like this. Well, obviously, the two elements are the same element. The two atoms are the same element. So there's no difference in the electronegativity. And no difference, meaning that it's a non-polar covalent bond. Okay, so right here you have the covalent bond, but it's also labeled as non-polar instead of being polar. Okay? And as you can see on the scale, as close to being 0 in terms of the difference in EN, or electronegativity, between the two elements, the more it can be described as a non-polar covalent bond. So I know this is just a lot of different terminologies, okay, and we're throwing all kinds of ideas together, right? I mentioned I began the tutorial with bond dissociation energy. That was just one, okay, and now you throw in electronegativity, right? You throw in octet group, you throw in ionization energy and electron affinity, and now you're talking about difference in electronegativity. Okay, in terms of what? Well, all these are models that help us explain chemical bonds. Right? Fundamentally, I said there are only 3 types of chemical bonds, either ionic, covalent, or metallic. Okay, we're going to talk about metallic some more, maybe next week. Okay, I mean the week after next. That's what I meant. Next week we'll just focus more on ionic and covalent. Okay, let's get those taken care of, and then we look at metallic bonding and see if we can develop a pretty good idea. Okay, what sort of element would tend to form metallic bonds? I mean, obviously the metal. And let's just say copper. If you're pure copper, okay, if you have a piece of copper, let's say a wire of copper, or I don't know, a piece of copper, a chunk of copper, okay, how would you describe, copper being a solid? Well, obviously you would have all kinds of, copper atoms, right? If this is pure copper, then obviously you have just copper atoms everywhere, okay? But how come, copper would have, certain so-called metallic properties? Like how come you can, basically pass electricity through copper? I mean, so we call this a conductor. When copper is conducting, but many other materials are not. Like plastic is not conducting. Okay, but copper is. So how come copper has this one of these metallic properties while the other materials don't have? Okay, so this is explained by an idea called metallic bonding. So obviously, okay, you can have just one element, copper, and you can speak of metallic bonding within the pure substance, copper. Okay, and it would explain sort of, how come copper behaves like a metal, and how come copper has all these various unique properties of metals. Okay, but if we are looking at something like sodium and aluminum, if they ever bond together, what kind of bond are they going to form? I don't know, maybe metallic bonding, okay, or maybe a little bit of covalent. Okay, ionic is very much not likely because they both like to, give up electrons. So sodium like to give up 1, aluminum on the other hand like to give up 3. Okay, why? Because of the octet group. Okay, and because they both like to give up electrons. None wants to gain electrons. Therefore, the covalent bonding idea does not really apply to the case of when the sodium, form a bond with aluminum. I don't know. I don't have a whole lot of examples of this, but maybe you can make an alloy out of aluminum and potassium. I'm sorry, sodium. You can make an alloy, but alloy is not a compound. Right? Alloy, remember, it's a mixture. So you're only mixing the 2 elements together. You don't bond together. What I'm talking about is, hypothetically, if you actually want to bond sodium and aluminum together, then it's got to be either a metallic bond or a covalent bond. It cannot be, an ionic bond. So there are all these, various things we need to be thinking about, while we are talking about chemical bonding. So I would suggest, we didn't really solve a lot of problems today or go over a lot of examples. But I assigned some online homework already. Okay, so hopefully that will give you an idea what sort of problems I expect you to be able to solve.
What do you have on
10 questions from chapter 9, that's it.
I mean, are you gonna have like bond association?
Yeah, it will be everything, yeah. I mean, if you feel like, okay, you just want to preview the questions and then maybe wait for a few lectures to pass by before you start doing it, or you want to just get started. But, you know, yeah, maybe initially you're going to feel like you don't know anything. But, you know, you keep using the help, I guess the show me, and then also the check my work option, you know, hints, and, you know, if you have access to ebook, maybe there will be a direct link between a particular online homework problem to the ebook, the correct ebook section. If not, then you just have to kind of remember, okay, this is all from chapter 9. It's all about chemical bonding. So I'm going to get really, really familiar with the ideas described in the chapter. Okay, I'm going to think about, okay, what's the difference between ionization energy and what's the difference between ionization energy and electronegativity. Okay, the two are obviously different, but how so? I mean, how would you compare the two? Okay, and what do these ideas tell you about the various elements on the periodic table? Okay, so I guess this is it. I don't really have too much more to talk about. Okay, just read chapter 9. Don't worry too much about Lewis structure. I know you already have an experiment on Lewis structure, but you revisit it. I mean, there is another experiment, okay, in the future that will go back to the idea of Lewis structure. Okay, how do you draw it, and what does it mean, and so on and so forth. Okay, so there will be a part 2. There will be a part 2 to molecular modeling. So don't worry about it too much if you cannot fully appreciate Lewis structures or molecular shapes by that same token. Okay, or the GSE okay. Well, I forgot to bring the attendance sheet, so if you can just indicate on the back of this piece of paper your attendance. Just put your name on this piece of paper. I would appreciate it.